Hello and welcome to yet another lecture on power generation and economics. Paper code EE704C. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is Unit Commitment Solution Methods. Today, we will discuss about dynamic programming solution. Lesson objective. After end of this topic, student will be able to understand the concept of unit commitment solution using dynamic programming. So today we will discuss about part 1 of the dynamic programming solution. So we are starting the dynamic programming solution part 1. So dynamic programming has many advantages over the enumeration scheme. The main advantage being a reduction in the dimensionality of any problem. Suppose we have found units in a system and any combination of them could serve the load. There will be a maximum of 2 to the power 4 minus 1, that is 15 combinations to be tested if there are 4 units are there in a system. So, if we apply the conception of strict priority order of 4 units depending upon the average fuel cost, we will produce a priority list, and this portion we will see later that how this priority list is produced, where unit 1, say there are 4 units and we will give unit 1, unit 2, unit 3 and unit 4. Unit 1 has minimum average fuel cost, average full load fuel cost, followed by unit 2, 3 and 4. So in our discussion of priority list method, we have seen that we have to give priority depending upon the average full load fuel cost. If unit 1 has minimum value of average full load fuel cost followed by 2, 3 and 4, so the priority will be given to unit 1, then unit 2, followed by unit 3 and last unit 4. So we have already known that the implementation of the priority scheme that is done on the basis of full load average cost, which would result in a theoretically correct dispatch and commitment if and only if the no load costs are zero. Unit input output characteristics are linear between zero output and full load. There are no other restrictions, and the startup costs are at a fixed amount. So these are the conditions for the correct dispatch, or in order to obtain the correct dispatch using the priority list arrangement. Those conditions are no load cost are zero, unit input output characteristics are linear between zero output and full load. There are no other restrictions. Startup costs are fixed amount. So in the dynamic programming approach that follows, we assume that a state consists of an array of units. A state consists of an array of units with specified units operating and the rest offline. The startup cost of a unit is independent of the time it has been offline. There are no costs for shutting down a unit. There is a strict priority order, and in each interval, a specified minimum amount of capacity must be operated. So, a feasible state is one in which the committed units can supply the required load and that meets the minimum amount of capacity each period. This is called a feasible state. A feasible state is one in which the committed units can supply the required load and that meets the minimum amount of capacity each period. So today we will discuss about forward AP approach. We will see that we have three cases. We will discuss on the one case today. One would set up a dynamic program algorithm to run backward in time, starting from the final hour to be studied back to the initial hour. In other way, one could set up the algorithm to run forward in time for the initial hour to final hour. One is called the forward in time from initial hour to final hour, and one is called the backward in time. It is from the final hour to come back to the initial hour. The forward approach has distinct advantages in solving generated unit commitment. For example, if the startup cost of a unit is a function of the time it has been offline, then a forward dynamic program approach is more suitable since the previous history of the unit can be computed at each stage. There are other practical reasons for going forward. The initial conditions are easily specified and the computations can go forward in time as long as required. So this is the another importance of going forward DP approach or forward dynamic programming approach. So forward means that the algorithm to run forward in the from the initial hour to the final hour. The general algorithm that we are using for forward dynamic programming approach is the recursive algorithm. To compute the minimum cost in our case with combination I is if cost ki is minimum of L and sum of P cost ki plus S cost k minus 1 comma L is to k minus 1 comma L is to k comma I plus F cost k minus 1 comma L, where the F cost ki is the least total cost to arrive at the state ki. It is the least total cost to arrive at the state ki. That is the minimum value of the cost, minimum value of the total cost. A, which stands for the state, and I, that stands for the combination that we will give. K stands for the hour, at which hour, and I is the state or the combination, and K is the hour. P cost Ki is the production cost for the state Ki. K is the is called the hour in hour K, and I is the combination. And S cost K minus 1 comma L is to K comma I is the transition cost from K minus 1 comma IL to state Ki. It is the transition cost from previous state to the next state. This is called the S cost. So here we are dealing with example 1. Here we are dealing with the example 1. So example 1, we will discuss an example in order to understand the conception of dynamic programming method. For this example, the complete search range will be used and 3 cases will be studied that I have already told, that case 1, case 2 and case 3. The first case that is we will study today, or I will discuss today, is the priority list schedule. The first case is the priority list schedule, and the second case is using the same example with complete enumeration. For both first two cases, we ignore the hot start cost and minimum up and down times. The third case that includes the hot start cost as well as minimum up and down times. 4 units are to be committed to serve an 8-hour load pattern. So there are 4 units are there and load pattern is for 8 hours. So there are 3 cases that we will discuss. For today we will discuss, for this lecture I will discuss about the only one case, that is the first case is depend on the priority list schedule, where we ignore the hot start cost and minimum up and down times. So this is the table for unit characteristics, load pattern and initial status for the case is in example 1. This is the general problem. It is given that 4 units 1, 2, 3, 4, which are used to serve the 8-hour load patterns 1, 2, 3, 4, 5, 6, 7, 8, and corresponding load demands are given here in megawatt: 450, 530, 600, 540, 400, 280, 290, and 50 for first hour, second hour, third hour, fourth hour, fifth hour, sixth hour, seventh hour, and eighth hour. So there are 4 units 1, 2, 3, 4, and their maximum demands are given 80, 250, 360 megawatt, and minimum are given 25, 60, 75, and 20 megawatt. The incremental heat rate that is given 10440 9000 8730 11900 for unit 1, 2, 3, 4, and the no load cost that is given 213 585.62 684.74 252, and the full load average cost are given 23.54 20.34 19.74 28.0. That is full load average cost, and the minimum times, that is the uptime 4551 and downtime 2341. We will neglect that particular part for our discussion of part 1, and that is the unit 1, 2, 3, 4. They are initial conditions. That is our offline and that is our online are given 5886, and it is also given that the hot start, that is 150, startup cost for 170, 500 and 0, and the cold for 350, 400, 1100, and 0.02, and cold start hour are 4550. So today we will also neglect the, I have already told that we are neglecting the hot start cost and minimum up and down time. So this portion we will neglect today, and this portion. So cold start we will consider that particular part, and the load pattern is also given. So, for the example one, that the units that must operate within its limit, startup cost for first two cases are taken as cold start cost that I have already told. The priority of the four units in this example is unit 3 to unit 1 and unit 4 we will discuss. And for the first two cases, minimum up and down time are taken as 1 hour for all the units. So, how the priority order of the units will be given. So, we have seen the from the data that we have given that the average fuel cost for the unit 3 is minimum, that is 19.74. So, it will give the first priority, followed by the unit 2 where the average fuel cost is 20.34, it will give the second priority. For the unit 3, the average fuel cost, that is 23.54, it will give the third priority. And for the unit 4, the average fuel cost is, average full load fuel cost is 28.00, so it will give the fourth priority. So depending upon the average full load fuel cost, the priority of the each unit is given, and this is come from the data that we have given, that the data is given in our example. From that we will, from the priority order, where unit 3 have a top priority, followed by 2, 1 and 4, and that is clearly written here. Unit 3, 2, unit 1 and unit 4 are given the priority. The priority order are given here. So, case 1 that we will study, where we will only consider the priority order scheme. So in case 1, the units are scheduled according to a strict priority order. So in this case, the units are scheduled according to a strict priority order. So that is, units are committed in order until the load is satisfied. The total cost for the interval is the sum of the 8 dispatch cost plus the transitional cost for starting any unit. We will see this particular portion. So, there is a state, unit combination, and maximum net capacity for combination. So, 1 that stands for unit is in operating condition or committed, and 0 that is the unit is uncommitted, means the unit is shut down. So there are unit 1, 2, 3, 4. There are 4 units. So 2 to the power 4 minus 1 that I have already told. There is a 15 combination that we have already get. This 15 combination. But the combination 1 means unit 4 is 1. Combination 2 means unit 1 is 1. And in this way, combination 15 means all the units are in on condition or committed. So unit combination 1 means combination 0, state 0 is not feasible because all the units are off condition. So state 1 means the unit 4 is committed. State 2 means unit 1 is committed. And in this way, state 15 means all the 4 units are committed. So the net capacity means it is a summation of maximum power of all the maximum capacity of all the units. We all know that the maximum capacity for unit 1 that is given in the data sheet is 80, For unit 2 is 250, for unit 3 is 300, and for unit 4 is 60. So when all those four are in committed state, the total maximum net capacity for the combination is 690. And when the unit 1, 2, and 3 is operating, so the summation of their maximum capacity, that is 80 plus 250 plus 300, it is given from the data sheet. So it will be, the total capacity is 80 plus 250 plus 300, it will be 630. So when unit 4 is along, it is 60 megawatt capacity. When unit 2 is at the state 2, when unit 1 is along, it is 80 megawatt capacity. So in this way, all the maximum net capacity for the combinations is calculated. Now, for the case 1, the only state examined each hour, that is consists of. So we will now see that this is the unit combination that we have already seen, and this is our load demand. So if I go through the each and our load demand, and the load demand for hour 1 to hour 8, we have told that it is a 8 hours load pattern. So if I see our load demand, it will see that from that particular data, the maximum load demand is 600 and minimum load demand is 280. So maximum load demand is 600 and minimum load demand is 280. So all the combination that we have tried, from there, the state 5 has 300 load megawatt load demand. It is always done on the basis of strict priority list. Again, I am telling, first we have to on the unit 3. So unit 3 is on at state 5, and the total net capacity, maximum net capacity for this combination is 300, which meet the minimum load demand 280. So state 5 is the feasible state. Followed by, we have to start the unit 2, depending upon our priority list in. So when unit 2 is start, so the combination is the state 12, where unit 3 and 2 are on condition and the total capacity is 550. Followed by, we have to start the unit 3, 2 and then 1, that is the 14th state. 3, 2 and 1 is on and the total capacity is 630. This is the state 14. And then we have to start the 4th unit. So the state 15, where unit 1, 2, 3, 4 is in on condition and total capacity is 690. So with the help of strict priority method, we will see which states are feasible for our calculation, that is 5, 12, 14 and 15 state. And these are on when the unit 3 is on, followed by unit 3 and followed by unit 2, followed by unit 1 and then followed by unit 4. It is done on the basis of strict priority method. And it is clear that the state 13 is not reachable in the strict priority ordering. So the state 30 we cannot be reached, because when we on the unit 2 and 3, 3 and 2, depending upon the strict priority method, here we on the, when you go from the state 12 to state 13, it is seen that at state 12, unit 2 and 3 are on, and in state 13, unit 2, 3 and 4 are on, but it's violating the strict priority method. So means after depending upon the full load average cost, so we have to, after 3 and 2, we have to on or commit the unit 1. So that's why you have to go from state 12 to state 14 where unit 2, 3 and 1 is on, followed by state 15 where unit 2, 3, 1 and 1, 2, 3, 4 are on. So that is why we state 13 cannot be reachable in strict priority order. So we have to calculate the incremental cost. So we have a linear function of FP, the cost function, where the no load cost is added with the incremental with the total production cost. So FP, the function of the cost is the no load cost plus it is a no load cost plus incremental cost into power. So the incremental cost is the FP minus no load cost, that is the function of fuel cost, minus no load cost divided by power. This is the general formula of incremental cost that we will apply in order to calculate the total cost. We will see it later. So the incremental cost is the cost function cost, means the total fuel cost minus no load cost divided by power. So let us calculate the incremental cost. So it is given from the data table, that the data table is given in the example 1. There are 4 units, 1, 2, 3, 4, and their maximum capacity are 80, 250, 360. And the full load average cost are 23.54, 20.34, 19.74 and 28. And the no load cost that is also given, that is 213, 585.62, 684.74, 252.00. So we have to calculate the incremental cost with the help of this formula. So for unit 1, the incremental cost is 23.54 FP, that is 23.54 into 80 minus no load cost minus 213 divided by total will be divided by 80. So it is clearly 23.54 into 80 minus 213 divided by 80 will be give 20.88. That is the incremental cost for unit 1. It is clear. For unit 2, the same we will calculate for the unit 2, unit 3 and unit 4, and it is given 18.00 for unit 2. For unit 3 it is 17.46. For unit 4 it is 23.80. So again for the unit 2 it will be 20.34 into 250 minus 585.62. Total will be divided by 250. It will give 18.00. For unit 3 it is 19.74 into 300 minus 684.74. Total will be divided by 300 will be 17.46. For the unit 4 it is 28 into 60 minus 252. Total will be divided by 60. It will give 23.80. The incremental cost for unit 1, 2, 3, 4 is calculated with the help of this formula. And those data are taken from our example. So the sample calculation for the case 1 is that if cost Jk minimum of, we have to find the minimum value of the cost. It is production cost P cost J comma K plus S cost J minus 1 comma L is to J comma K plus F cost J minus 1 comma L. So we have available states that we have already seen, that 5, 12, 14 and 15. From there, the initial condition L is taken as state 12. So we have to calculate for the each hour. Say for the first hour, we have three states, say 15, 14 and 12. So we have to see that which among those three states, which state has the minimum cost. We will see it. So our allowable state using the conception of least, using the conception of priority scheme method, that is 5, 12, 14 and 15, and L which stands for, J stands for the hour and K stands for the state and L stands for the initial condition. So why state 12 is considered as initial condition, that is L equal to 12, why not state 5? Because if I see at state 5, for the hour work, first we have to see for the hour work, because we have to go hour by hour calculation that I have already told. For the first hour, our load demand is 450. For the first hour, load demand is 450. So state 5, that is when unit 3 is only in operating condition, it can produce 300, maximum 300 megawatt capacity. So this cannot meet the load demand for the first hour, that is 450 megawatt. But state 12, when unit 2 and 3 are in on condition, the capacity is 550, so it meets the load demand of 450. So that's why we neglect the state 5 for first hour and we are taking state 12 for the first hour, or state 12 as an initial condition. So these are the sample calculation for the case 1, where for the first hour we just put the k value of 15, so it will be 1 comma 15, that is the first hour and the 15 state, and the production cost of the first hour and the 15 state plus is cost of, that is the that it is given, that is a k minus 1 in our previous discussion. So it will be j minus 1, that will be the 1 minus 1, that is 0th hour, and the state will be L, that is 12. It is a transition cost from 0 hour to first hour and from 12 state to 15 state. So this is called the transition cost, the S cost, and P is the production cost. So that is, it is clearly given when j equal to 1. So j minus 1, from here when j equal to 1 and k equal to 15, it is the production cost of 1 comma 15 and transition cost of 1 minus 1, that is 0 comma 12 to 1 comma 15, from 0 state to, from 0 hour to first hour, and the from state 12 to state 15, how much that transition cost is there, and we have to find the minimum value of the total cost. So it will be calculated for 15, for 14 and for 12. So this is the, from there which one is the minimum, that is 9208 is the minimum, and we have to take this value for the first hour. So in this way we have to calculate for the first, second to up to 8th hour. So the calculation is like that. This is the load pattern for the first hour. It is the load we have to meet by 450. So that is the first hour, j equal to 15, k equal to 50, j equal to 1. That is the first hour. J stands for hour and k stands for state. That is k equal to 15, and L stands for initial condition. That is the 12 state. So there are the 4 units 1, 2, 3, 4, and their maximum and the minimum demands are taken from the data sheet. So the first hour the load demand is 450. So the load demand is 450. So this is the average fuel cost that is given in the data sheet. So from that average fuel cost, it is clear that which having a minimum average fuel cost, it will be loaded more. So and which have a maximum fuel cost, it will be loaded less. So it is clear that this one that is 28.0, that is the unit 4 has a maximum average full load average cost, so it will be loaded less. So the minimum loading is given to it, it is 20 megawatt, and unit 3 has a minimum value of the full load average cost, so it will be loaded maximum, so that is 300. So remaining will be the 130 because 450 minus 320 will be 130. From those two, it is seen that unit 1 has a maximum value of the average fuel cost, so it will be loaded less, so it will be loaded with minimum capacity, that is 25. So 130 minus 25, that is 105 will be loaded by, will be given by the unit 2. So in this way the load sharing is done in order to meet the 450 load demand. So now this is the node. This is taken. This table is taken from the data that we have already given for unit 1, 2, 3, 4, and the load sharing is given that we have already calculated 25, 105, 320, and the full load average cost that is given 23.54, 20.34, 19.74, and 28. Startup costs are also given. That is 350, that is the cold start. For the cold start, the startup cost 350, 400, 1, 100, and 0.02. And that is the no load cost is given 213, 585.62, 684.74, and 252. And the incremental cost that is we have already calculated, that is 24.88, 18.0, 17.46, and 23.80, that we have already calculated that particular part and we are from a table. So the no load cost is the summation of these 4 costs 1, 2, 3, 4. This is the summation of those 4 costs. We will give that given that the value of the no load cost at J first hour, K equal to 15 and N equal to 12 is the 1735.36. So we are taking this particular formula. So the production cost for state 1, 25 is the F1 25 plus F2 105, that is F1 25, that is unit 1, 25, that is the power that is sharing by the unit 1, and F2 105, F3 300, and F4 is the 20 plus no load cost. So we already know that this is this part that we have already seen, that how the load is sharing for the first hour, and for the K equal to 15 state. So it will be 25 into 20.88, 25 into 20.88. It is the multiplication of power that is given by that particular unit 1 into the incremental cost. So it is 25 F1 is into 25 F1 means the incremental cost. So it is 20.88 into 25 followed by F2, that is 18 into 105. That is how this is done. The production cost, it is the power that is delivering or the sharing by that particular unit. Say for the unit 1, it is sharing 25 megawatt and the incremental cost is 20.88. So it is the multiplication of load sharing, that is 25, into incremental cost, that is 20.88, and it will be done for the each unit. And in this way, for unit 3 and unit 4, plus the no load cost, that is 1735.36, the total will become 9681.36. This is the total production cost. And the startup cost, that is from 0 hour to first hour, and the state changes from 12 to 15. So when the state is changing from 12 to 15, means when it is at 12 state, the unit 2 and 3 is on. So when it is going to 14 state, that means we on unit 1, and startup cost for the unit 1 for cold start is 350. And when we are going from 14 to 15 state, we on the unit 4, and the startup cost for the unit 4 is 0.02. So that is 350 plus 0.02, that is the total transition cost that we have already calculated is 350.02. That is the total transition cost from going from state 12 to state 15 for first hour. At state 12, only unit 2 and 3 is on. When it goes to state 14, unit 1 is on, and corresponding cold startup cost for the unit 1 is 350. We add 350. And when it is going from 14 to 15, unit 4 is on, and for the unit 4, the startup cost is 0.02. So we add 0.02. So total will be 350.02. So the total fuel cost become, or the total cost that is become summation of this cost and this cost, it will become for the j equal to first hour k equal to 15 state, the total cost is 10211.38. This is the way we calculate for the j equal to 1, k equal to 15, and n equal to 12. That is the first hour state 15. Now for the first hour state 14, and the initial condition is 12. So load demand, then we have to make the 450. So here it is clear that there is, when at the first hour equal to 14 state means the 3 units are on, that is unit 1, 2 and 3. K equal to 14 state means k equal to 15 means 4 units are on, k equal to 14 means 1, 2 and 3 are in on condition. So 1, 2 and 3 will share the load for the first hour, that is 450. So here again, from the conception of full load average cost, the minimum value of the full load average cost for the unit 3, so it will share the maximum, that is 300, and remaining 150 will be shared by unit 1 and 2. From these two, unit 1 has a maximum full load average cost, that is 23.54, so it will be run at its minimum value, that is 25, and 125 will be given by the unit 2. So that is for the state k equal to 14 and hour j equal to 1. So the simple no load calculations are these three. These three values will give the no load cost. This one 1483.36. So the production cost will be same calculation, that is 25 into 20.88 plus 125 into 18.00 plus 300 into 17.46 plus the no load cost, that is 1.1483.36. So the total cost will be 9493.36, and the startup cost, that is from the initial state 12 to 14 only. We start for the initial, for the state 12, unit 2 and 3 is on, and for the state 14, unit 1, 2, 3 is on. So we have to only start the unit 1. So the startup cost for unit 1 is 350. So total cost will be 9. That is the summation of two costs, this one and this one. So the total cost will be 9843.36. is called the transition cost from 0 to 12 to 1 to 14. Only unit 1 is on, if I say this particular type, this one. At 12 step, unit 2 and 3 is on, and 14 step, we on the unit 1. So the startup 1, 2, 3 is on. So means we just added unit 1. So startup cost for the unit 1 is 350. So the transition cost will be 350. So again, for the first hour, when k equal to 12 and L equal to 12, that we have already seen that for that particular j equal to 1, k equal to 12, and L equal to 12. So k equal to 12 means only unit 2 and 3 is there. So unit 2 and 3 will be supply the load demand for the first hour, that is 450, and it will be clear that it will be run at its maximum value 300 and it will be give 150. It is very clear depending upon the full load average cost. So again, the no load cost will be calculated these two parts to give the no load cost, and the production cost will be 150 into 18.00 plus 300 into 17.46 plus this one no load cost 1270.36 will give 9208.36, and then there is no transition cost, so it will become 0. So the total cost became 9208.36. So it is clear that for the state 15, for the state 15, the total cost is 10211.38. For state 14, the total cost is 9843.36. And for state 12, the total cost is 9208.36. So for the first hour, the minimum cost will be this one, 9208, and it is given by that state 12. So for the first hour, we have calculated that the minimum cost is 9208 and it will be given by the state 12. So in this way, we have to calculate for each hour up to 8 hours. So for the second hour, there is J equal to the load, depending upon the load demand, that is the load demand is 530. So depending upon the load demand, the feasible states are 12, 14 and 15. The feasible states are 12, 14 and the 15 because the load demand is 530. So this, the state 5 cannot be meet the load demand. So the feasible state is, as the load demands is lie between 550 to 690, that is 530. So the feasible state is 12, 14 and 15. So we are taking two strategies are set at each stage, that is n equal to 2. So we are taking the initial conditions 12 and 14. So for k equal to 15, the total cost will be 215 to minimum of 12 or 14 for which state at our j equal to 2, for 12 state or for 14 state, which cost is minimum, we will take that particular cost. So first we have to calculate the production cost. So it is clear that the load demand is 530. For the load demand of the 530, the unit 4 will be the minimum value, that is 20, because it has maximum full load average cost. Then it has minimum full load average cost. Unit 2 will be 300. So 530 minus 320, it will become 530 minus 320, that is become 210. So unit 1 and 2 will be shared the 210 load. So from here, unit 1 will be having maximum full average cost. Between unit 1 and 2, 1 has maximum. So 1 will maximum full load average cost. So 1 will give the minimum value, minimum power, that is 25, and rest 210 minus 25, that is 185, will be given by the unit 2. So the total cost will be the summation of all the no-load cost. The summation of all the no-load cost. That is 2135 plus 585.62 plus 684.74 plus 252, that is 1735.36. So this is the general formation. So the production cost will be if 120, that is 25 into that we have already known, into 20.88 plus 18 into 185 plus 17.46 into 300 plus 23.80 into 20 plus the no load cost, that is 1735.36, that is equal to 11301.36. So here that is 11301 and we are taking plus minimum of, now we will go for the transition state. In 15 state we will go for from 14 to 15 and from 12 to 15. If I go from 12 to 15, for the 12 state that this calculation is taken from the previous 9208, and when you go for the 12 to 15, at 12 state unit 2 and 3 is on. So when you go from 12 to 14, we have to on the unit 1. So its startup cost is 350, that is 350. And from unit 14 to 15, unit 4 is on and its startup cost is 0.02. So it is 0.02. So 350 plus 0.02 plus 909208. That is from unit 12 to 15, because we have two initial states, that is unit 12 and unit at we have two initial states, that is 12 and 14, that we have seen equal to 12 and 14, because we are taking both two at a time. So we are two strategies that we are saved at each stage. And now that is we are moving from 12 state to 15 state. And now we are moving from 14 state to 15 state. When we are moving from 14 to 15, at 14 unit 1, 2, 3 is on, and at 15 unit 1, 2, 3, 4 is on. So we now, when we are moving from unit state 14 to 15 means we have to on the unit 4. So unit 4 is 0.02 and this 9843 is come from the previous value of state 14, and this is 9208 is coming from the previous value of state 12. So summing this will be the minimum value, first one. So 11301 plus this value, it will be give 20859. That is the minimum value for the hour 2 and the state equal to 15. This is the minimum value. In this way, we will calculate the each and every state, and for each and every hour we have to calculate in this particular way. So this value will give us 9558.08, and this is, so it is less compared to this value, and 11301 plus this value will get the value of this one, 20859. So in this way you have to calculate for each hour, and for each hour at each state we have to calculate, and from there we have to find the minimum value. From there, using that particular conception, that is this one, for each hour we have to calculate and we have to find the minimum value. Minimum value means the minimum cost value for each hour. We have seen for our first hour, the minimum value is given by the state 12 that we have already seen. State 12, that is 9208. So in this way, we have to calculate for each hour and we have to find the minimum value. So we will give that for hour 1 that we have seen, that 12 state will give 9028. For hour 2, same 12 state will be given 19857. For hour 3, 14 state will be given 32472. And for 4 state, the 12, the minimum value will be given by the 12, that is 433300. So in this way, we have to calculate the entire phenomenon that is dependent on the, in this way we have to calculate for the 8 hours. So the total cost for the case 1, that is the priority order that we have considered, and up and down times are neglected, are 73439. This is the cost for the case 1. The case 1 that we are considered only the priority list scheme or the priority order. So the total cost is 73439. So today we have learned about the dynamic programming solution, that is the dynamic programming solution, and we will see the forward BP approach. And we are considering the part 1 that we have learned, where we have only considered the priority list or the priority order. So today we have seen how a problem can be solved with the help of dynamic programming solution. Thank you.